Welcome back. In 4.4 we look at two of our favorite ideas, continuous functions and compact sets, and great things happen when we put them together. There are two big ideas in this section. First, if a function is continuous on a compact set, then the range of f will also be a compact set. So a continuous function maps compact sets to compact sets. A consequence of that is going to be the extreme value theorem, which is very important for us in calculus. The second big concept for today is understanding an idea called uniform continuity. This is a nicely behaved continuity. And it turns out that if I have a function that is continuous on a compact set, then my function f is actually very nice. It is uniformly continuous. So these are some nice properties of compact sets. Let's begin. Let f be a function from a to the reals, let it be continuous, and suppose that b is some subset of a. We say the image of b under f is f of capital B, so I don't know if we've used this notation before, but f of the whole set is just f of x such that x is in B. So we want to know what kind of properties of B are shared by f of B. If B is open, must f of B be open? If B is closed, must f of B also be closed? How about the first one? If B is open, must f of B be open? What do you think? That's right. The answer is no. Consider, for example, f of x equals x squared on the open interval from -1 to 1. What is f of b? Make your guess. And it is the interval that contains 0 but does not contain 1. And that is not an open interval. How about the next one? If b is closed, must f of b be closed? What do you think? Right again, the answer is no. Here's an example. Let f of x equal 1 over 2 to the x on the closed interval that starts at 0 and goes to infinity. What is the range of this? What's the image of b? It's the interval from 0 to 1 that does contain the right endpoint but not the left. So that is not a closed interval. So we've failed with the open sets, we've failed with the closed sets. Is there some other quality that b might have that is shared by f of b? And the answer is yes. If b is closed and bounded, then f of b must be as well. So here it is. Here's our first big idea, the preservation of compact sets. Let f be a function from a to r. Let it be continuous on domain A. If k contained in A is compact, then f of k is compact as well. We're going to need to know the definition of compact, so let's remember, intuitively we think that k is closed and bounded. But the actual definition says, for every sequence of x's in k, there's some subsequence that converges to a point x that's also in k. So we will need that. To prove 441, here's what we'll do. We're going to take a sequence of y's that are in my range and show somehow that there is a subsequence of those y's that converges to some point that is also in my range. Okay, so let y be a sequence in f of k. Here's how I think about it. K is this closed compact set in my domain. And it maps to a bunch of y values in my range. So that set of y values, is that compact? Let's take a sequence of y values in that range. So y1, y2, y3, and maybe these y's are getting closer and closer and closer at some point. For each n, there is at least one x sub n in my k, such that f of x sub n is y sub n. Since k is compact, there's a subsequence of those x's that converges to x that's actually in my set k. f is continuous at x. This was part of my hypothesis. So the sequence of function values at the subsequence of x's converges to f of x. F of x is in my range. So the sequence of y values, which is nothing more than the function values of the x's, the sequence of y values also converges to f of x, which is in my range. And that's it. My f of k is compact. Any sequence of y values converges to some value that is also in my range. A corollary to this is the extreme value theorem. Before stating the theorem, let me talk about something that's conceivably true, but actually ends up not being true. Conceivably, as we imagine our x values moving from left to right, I have corresponding y values that increase. They almost reach some value, then come back down again. Say 5. They almost reach 5, but never quite reach 5. Is that possible? Is it possible that the range of my y values is actually open on one end? And the answer is no. We saw that compact sets must map to compact sets. If f is a function that goes from k to r and is continuous on a compact set k, then f attains a maximum and minimum value. It really will attain this value at the maximum. So in other words, there exist some x0 and x1 in my k, such that f of x0 is less than or equal to f of x is less than or equal to f of x1 for all x in k. In the picture, my x0 would be on the left and x1 somewhere down. I really can plug in the 1 and get out the very highest value. The author of our book calls this an extremely important theorem, and it's a joke, yes, but it also is true. I was looking at one point at my calculus theorems. So here are the theorems that we go through in calculus in order to prove the fundamental theorem of calculus. And the very first thing that we need is the definition of the derivative. But look at this, EVT, extreme value theorem. The extreme value theorem is a foundation for all the theorems that we use when we prove in calculus. We use the extreme value theorem to prove Rolle's theorem. And the extreme value theorem is used to prove the fundamental theorem of calculus part 2. So it is a joke. It is extremely important, but it is also true. The extreme value theorem is a fundamental theorem of calculus. Let's talk about our second big idea for today, uniform continuity. Here are two functions, f of x, 3x plus 1, g of x is x squared. 3x plus 1 is uniformly continuous. X squared is not uniformly continuous. Let's see how they are different. F and g are continuous on the set of real numbers. That means that for all real numbers c, f and g are continuous at c. Remember, we first defined continuity at a point c, and then we say a function is continuous on a domain if it's continuous at every point in that domain. So how do I go about showing that f is continuous on all reals? I have to show that given any c, that the absolute value of f of x minus f of c is small whenever x is near c. We've done proofs like this in the past where c was some particular number, like 5 or 7. But now let's just leave it as a variable, c. Well, the expression absolute value f of x minus f of c simplifies to 3x plus 1 minus 3c plus 1, and that turns into 3 times the absolute value x minus c. This gives us a little clue about what our delta should be. Let epsilon greater than 0 be given. Choose delta to be epsilon over 3. Now, if absolute x minus c is less than delta, we find the difference in the function values equals 3 times x minus c, and that's less than 3 times epsilon over 3, which is the epsilon. And there's our proof that the function 3x plus 1 is continuous on all the real numbers. Let's turn our attention now to x squared. Given any c, let's show that the difference in function values is small whenever x is close to c. So as before, we're going to look at the difference, g of x, the absolute g of x minus g of c, and turn that into some expression. We get absolute x squared minus c squared, and that factors x plus c, x minus c. X minus c is what we want to make small. It would be great if I could find a bound on x plus c. A bound on x plus c. Well, here's the trick that we do. We imagine that delta is less than or equal to 1. So if I force delta less than or equal to 1, x minus c is less than 1, that will show a certain bound. So absolute x plus c is less than or equal to absolute value of x plus absolute value of c. That's just the triangle inequality. But now this absolute value of x turns out is less than absolute c plus 1, and that comes from our assumption up above. There are some details you could work out, but I'll skip those for right now. Okay, at this point we can simplify the expression, and this turns into 2 absolute c plus 1. So that is our bound on x plus c. So maybe that gives us a clue about what delta should be. Let epsilon greater than 0 be given. I will choose my delta to be the minimum of 1 and epsilon over 2 absolute c plus 1. Now, if x minus c is less than delta, what do we know? The difference in the function values factors as x plus c, x minus c, so that was just algebra, we haven't used our delta yet. But since delta is less than 1, I have a bound on the x plus c, and since x minus c is less than epsilon over 2c plus 1, we get that this expression is less than 2c plus 1 times epsilon over 2c plus 1, and that is just epsilon, which again, that was what I needed. So we've shown continuity for these two functions on all the real numbers. What's the difference? The big difference is this. In the first example with f, when I chose my delta depended only on epsilon and it did not depend on c. This delta worked for an epsilon for any c. But look at the case down below in g. In g, when I chose my delta, that delta depended on epsilon and it also depended on c. Normally when we think about a proof of continuity, you say, given epsilon, there exists a delta such that blah blah blah, and we think delta is chosen as a function of epsilon. Given an epsilon, you find a delta. But in fact, when you're showing continuity at a particular point, delta is often a function not only of c, but it depends on the point that you actually choose as well. Well, here's what's so nice about our first example, is that the delta we chose doesn't depend on c at all. This delta works for epsilon no matter what the point under consideration is. And that's the nice feature of uniform continuity. A function is uniformly continuous if, given an epsilon, there's some delta that makes the proof work regardless of the choice of c. Here's a slide that I was going to spend some more time on, but I think in the interest of time, I'll skip it for now, but you can pause the video if you would like, soak it in, and then we'll continue. Here's our definition for uniform continuity. A function f going from a to the reals is uniformly continuous on a if, for every epsilon greater than 0, there is some delta greater than 0, such that for all x and y in my a, if x and y are within delta of each other, then f of x and f of y are within epsilon of each other. I'm not using c anymore. I'm not focusing on any one particular point. I'm just requiring that my two inputs, x and y, be really close to each other, and as a consequence, my two outputs, f of x and f of y, are also very close to each other. The function x squared is not uniformly continuous. That was the g that we just looked at previously. The idea is, as I move to the right, that x and y being close to each other, xy, xy, the function values are going to get more and more spread out. as I go. However, the function x squared is uniformly continuous on the closed interval from 0 to 2. And this is an important distinction. Uniform continuity is not a characteristic of just a function, it's a function and a domain. We talk about a function being uniformly continuous or not uniformly continuous on a particular domain. Another example, sine of x, it is uniformly continuous on the set of real numbers. You think about the slopes of this curve. The slopes are bounded. The slopes never get more than 1 or never less than -1. So the fact that my slopes are bounded maybe helps us think that it's going to be uniformly continuous. The function sine of 1 over x is not uniformly continuous. And again, thinking about slopes, we have this sense that as I move from the right to the left, the slopes of this function are becoming arbitrarily large. Let me pause for a moment to emphasize the importance of this definition. It's a weird definition. It really takes a while to work with and think about to make it feel right to you. So look at these 4 examples and see if you can start getting an intuitive feel for what it means to be uniformly continuous on a domain or not. Right now, let's go through a couple proofs showing that functions are uniformly continuous. So here's our definition again, just to keep in mind, and we'll start with our first example. The cube root of x is uniformly continuous on all the real numbers. Why is this so? Well, I'm going to use a fact. If a is less than b, then the cube root of b minus the cube root of a is less than or equal to the cube root of b minus a. A picture makes this pretty evident. In this picture, I've chosen some a and a b, and correspondingly there's a cube root of b and a cube root of a. And we can imagine taking that difference, a and b, and sliding it to the left. So the distance that a is from b is the same as the distance that 0 is from b minus a. But what happens is, upon sliding to the left, that space between the function values opens up. And this actually ends up giving us a little bit of a clue for what our choice of epsilon should be. Let's imagine that an epsilon is given, and I want to find one delta that works for this particular epsilon wherever I am in my domain. Well, the trick is, let's slide that epsilon down. Maybe that's my epsilon there. And I notice that, let's see, what is that? That'll become now the epsilon cubed. If x and y are within epsilon cubed, then the cube root of x and the cube root of y are within epsilon. And that works no matter where I slide my x and y. If x and y are within epsilon cubed of each other, then certainly their output values are within epsilon of each other. Okay, let's continue on to the actual proof. Oh, and this fact, I'll give a formal proof of that in a couple slides, but I'll not dwell on it. So let epsilon greater than 0 be given. Let delta equal epsilon cubed. Choose any x and y in the reals where x and y are within delta of each other. Without loss of generality, we may assume that x is less than or equal to y. So x and y are just 2 numbers. Whichever one is the smaller of the 2, call that x, and whichever number is the bigger of the 2, call that one y. So y minus x is less than epsilon cubed. Now, the difference in my function values, I want to show that this guy is less than epsilon. Well, plugging in what f of x and f of y are, we get this expression. Since y is greater than x, I can remove absolute values and switch the order around. Here's where I use the fact about the inequality with cube roots. And now here is where I use the fact that y minus x is less than epsilon cubed. So I can replace the y minus x with epsilon cubed and get something a little bit larger. Well, of course, the cube root of epsilon cubed is epsilon, and there we have our proof. The difference in the function values is less than epsilon. Here's a quick proof of the cube root inequality fact that we used before. I will not dwell on this, but if you'd like to pause the video and go through the steps, please do. Moving on. The sequence criterion for absence of uniform continuity. We like to be able to prove that some functions are uniformly continuous. Also, it's nice if I have a tool to prove that a function is not uniformly continuous. And this is a nice way to do it. The sequence criterion for the absence of uniform continuity. A function f going from a to r fails to be uniformly continuous on a set A if and only if there exists some epsilon naught greater than 0 and two sequences xn and yn in my set A such that corresponding sequence terms get closer and closer to each other. The difference of corresponding terms goes to 0, but the difference of corresponding function values of those terms stays above my limit epsilon naught. So if I can make two sequences where corresponding terms get closer and closer together, but those function values stay above a certain limit, then the function is not uniformly continuous. Here's sort of the idea seen with x squared. I can have an x1 and a y1 and an x2 and a y2 and an x3 and a y3, and you'll notice I've tried to draw it so that x1, y1, they're close together, x2, y2 a little bit closer, x3, y3 closer yet. But what's happening when I plug those numbers into my function? The function values are spread apart. In the second case, the function values of x2 and y2 are still spread apart a little bit more. The function values on x3 and y3 are still spread apart. So if I can do that, if I can make a sequence of pairs of terms where the pairs are getting closer and closer together, but the function values don't ever squeeze in together, then that's exactly what it means for my function to not be uniformly continuous. Recall the definition for uniform continuity, and here's the negation of that definition. F is not uniformly continuous on A if there's some epsilon greater than 0, such that for any given delta greater than 0, we can find some x and y in the reals where the difference of x and y is less than delta, but the difference in the function values is greater than or equal to that epsilon naught. Here's a quick little proof for the theorem. So the theorem is if and only if, and we'll start by proving the leftward implication. Let's suppose that a sequence xn and sequence yn exist, then my function f is not uniformly continuous. This is pretty straightforward. We can plug in the xn and the yn in for x and y, and we can see that my x's and y's are getting closer together, but the function values at the sequence terms stay apart. So actually, that is pretty direct, and there's not much more to say. How about the other direction? Let's suppose that my function f is not uniformly continuous. Can I show that there exist these sequences? Well, if it's not uniformly continuous, then for any given delta greater than 0, we can find x, y, blah, blah, blah. So in particular, for delta equal to 1, I can find x1, y1 that are within delta of each other, and where the difference of my function values is greater than that epsilon naught. And in general, given any delta, how about delta n equals 1 over n? I can find an xn and yn where the difference of x and yn is less than delta, but the difference of the function values is greater than the epsilon. So that's it. So we can really create these sequences of x's and y's. Now, let's use this theorem. Let's use the sequence criterion for absence of uniform continuity to prove that a couple sequences are not uniformly continuous. And in order to do that, we will use the leftward implication. Given a function, I will show that these sequences exist in order to prove that the function is not uniformly continuous. First example, let's prove that x squared is not uniformly continuous on the set of real numbers. Consider epsilon naught equals 1. Our choice of epsilon naught is a little bit arbitrary. 1 usually seems to work, so give it a try. We need to find two sequences such that the difference in corresponding terms approaches 0, but the difference in the squares of those guys always is greater than or equal to 1. So you can think about this for a little bit and see if you can come up with a sequence. I'll just jump right to the answer. Consider this. I mean, there are other solutions, but here is one solution. Maybe xn is n plus 1 over n, and yn is just n. So you can see that if I just take a difference of those two things, it's 1 over n, that gets smaller and smaller and smaller. It goes to 0. But what about the difference of the squares? Well, xn squared is n squared plus 2 plus 1 over n squared, and I'm going to subtract off an n squared. I just end up with 2 plus 1 over n squared. As my n's increase, that gets smaller and smaller, but it always stays above 2. My epsilon naught was 1, so that works also. That's always greater than my epsilon naught. That's it. We just proved, by finding these two sequences, we just proved that the function is not uniformly continuous on the reals. Another example. Let's prove that h of x equals sine of 1 over x is not uniformly continuous on the open interval from 0 to 1. Again, let's just make epsilon naught equal to 1. We can modify it later if we need to. The maximums of this function occur at 1 over these values when regular sine achieves its maximum. So x1 is right there, x2 is that point on the x-axis, x3, and so on. The mins of this function occur at these particular values. So there's a y1 and a y2 and a y3. And we can make a couple pretty quick observations. The difference of xn and yn is going to go to 0. In fact, these two functions, these two sequences individually go to 0, so certainly their difference goes to 0. But also, h of xn minus h of yn, it's always 2. The xn's have a value of positive 1, and theyn's have a function value of negative 1. So whenever I take a difference, the answer will always, always, always be 2, which is always, always greater than epsilon naught. So we've proven that sine of 1 over x is not uniformly continuous on the bounded interval from 0 to 1. All right, our last theorem. Let's remember this example. 1 over x, it was not uniformly continuous on 0 to 1, but what if I have some function over the closed interval from 0 to 1? Must that be uniformly continuous? Theorem 447, uniform continuity on compact sets. Let K be a compact set. If F is continuous on K, then F is uniformly continuous on K. The proof isn't bad. Suppose that F is not uniformly continuous on K. So this is a proof by contradiction. And apply the SCAUC, the sequential criterion for absence of uniform continuity. That tells us that there exists an epsilon naught greater than 0, and there exist two sequences, a sequence of x's and a sequence of y's, such that the corresponding sequence terms are getting closer and closer and closer to each other, but the function values at those terms stay apart by at least epsilon naught. Well, my set K is compact, and so this set of x's must have a subsequence that converges to a value x that's also in K. Now, there's a corresponding subsequence of y values, ynk. What happens to those? Well, since the difference in my corresponding terms goes to 0, it turns out that the subsequence of y's also converges to x, that same x that the x's converge to. So my subsequence of x's and my subsequence of y's both converge to the same value x in K. My function f is continuous, so by using the sequential characterization of continuous functions, I know that the sequence of function values at the x's approaches f of x, and the sequence of function values at the y's approaches f of x also. Well, let's take a difference of these two sequences. The limit as f of the x's minus f of the y's, that thing has to go to 0. But now I've reached my contradiction. Good thing I'm at the bottom of the slide. I don't have much more to go. This contradicts the fact I had known that the difference in my function values had to be at least as big as epsilon naught, but at the same time I'm seeing that the difference in my function values goes to 0. These can't both be true. There's the contradiction, and that proves the theorem. Whew. I know there was a lot today. Thank you for sticking with me. If you're still sticking with me at this point, the both of you, I really appreciate it. Let's take a look at the homework. There it is. For problem 2, please don't just answer yes or no. The question says, are these functions uniformly continuous? But actually prove your answer. And here's a little hint for 2C. All right. Again, thanks for sticking with me. I know it's a lot of material. The biggest advice I would say is go back and look at this definition of uniform continuity. It's subtle, and it takes some time to grapple with, but that's what the homework problem's there for. So give them a try, give them your best effort. Ask me if you have questions. All right. I'll talk to you later. Bye.